This video is for those students who missed the lesson on September 8th in IB1 Block E. We're going to cover the relationship between acceleration and displacement, as well as the speed of the particle moving in simple harmonic motion. It's part of topic 9.1. Now this is a picture of something we did already in class when we talked about the acceleration in simple harmonic motion and how it moves about. And one of the things we said is that if something is speeding up in a positive direction, we get positive acceleration. So from here, from A, as the pendulum swings to C, that's what we'd get. It's speeding up, and I've noted here that positive means to the right. Then as it moves from C to D, we have it slowing down again in a positive direction. So that's going to be negative acceleration. But now as it swings back from D to C, it's speeding up in a negative direction. Speeding up in a negative direction is also negative acceleration. And now finally, we have it slowing down from C to A in a negative direction. That is positive acceleration. So let's take a look at what we've got here. We have, if it's on the positive side of the equilibrium, we have a positive x. If we have it on the negative side of equilibrium, we have a negative x. And if you take a look, we've got a relationship here. Every time that it's on this side of equilibrium where the x is positive, I've said there's a negative acceleration. Likewise, on this side of equilibrium where my x or my displacement is negative, I have a positive acceleration. So what that gives me then is a relationship that the acceleration is proportional to negative x squared. And that negative is that when they have positive acceleration, I actually have a negative displacement. And we've talked about before when we first did this slide, how the farther you are away from the equilibrium, the greater the acceleration is. Remember, the greater from equilibrium would be the greater the force pulling it back, the restoring force, and with F equals ma, that gives us a greater acceleration. I have the greatest acceleration at A, I have zero acceleration at C, and again, a great acceleration at D. Now, if I want to take this from a proportion and create an equation, there's going to be a constant in there. And in fact, what it is A equals negative omega squared x. And so you might say, well, what is omega? Well, it means the angular frequency. And we're going to have more of that when we do topic 6. But for now, what I want to point out is that omega equals 2 pi f. Or since the frequency and the period are inverses, I could also say 2 pi divided by the period. This last part of the equation is in your data booklet. You need to look into section 9.1 for simple harmonic motion. The SL course tends to do this all with just talking about qualitatively what the motions are, left to right, speeding up, slowing down, but the HL has to do this with equations. So if I want to put that back in, I can then calculate my acceleration if I know my frequency and how far I am away from the center. One last thing I want to point out about the acceleration is how we describe it. If I'm at A here and I'm talking about the acceleration, I've said it's the greatest, and we would say it's directed towards the center, right? It's a positive acceleration, so it must be in this direction. Likewise, if we're over here at D, we'll say it's a negative acceleration for all the reasons we've said, speeding up in a negative direction, but we would also say it's directed towards the center. Okay, so let's take a look at an example of using this. So first of all, anytime you have a graph, please carefully look at it and say, what are on the axes? Because that will tell us a lot about the kind of information that we can get from it. This is a displacement time graph. So first of all, what is the amplitude of the motion? And I'm going to read that either right here or right here. And I can read it from the graph, and that means my amplitude is going to be 6. Make sure you use units, meters. What is the time period? Well, because this is a distance time graph, that means I can just go from 2 points in phase. So I can go from a peak to peak and find the time between there, or I could do from this point here to this point here. It'll give me the same value. My time period is going to be 8 seconds. Now, calculate the frequency of the bounces. Frequency is going to equal 1 over the time period, so that'd be 1 over 8. But remember, this is measurements, and we are not dealing with perfect values like you would in math land. So we actually should write this as a decimal. And I'm going to suggest that we should only have 2 significant figures, never write less than that, due to the accuracy of the diagram. Now it says use your values to work out the maximum acceleration. Remember we said that a equals negative omega squared times x. So what we need to know is, where does our maximum acceleration occur? Well, the maximum acceleration will occur at maximum displacement, which we call amplitude. And here we can put in the omega is going to be 2 pi f, or I can say 2 pi over t, which will be 8 squared times my maximum, which is 6. Pick up your calculator, and I'm sure you can get the answer. Okay, one last question. Notice again, what kind of graph is this? Oh, we've never talked about this. Energy displacement. But when you see something different, you say, Mrs. Henderson isn't crazy. How can I still answer this question? And the answer is, you read the graph and think about how it relates to what we're doing. If we have a displacement of 0, so that means it's going to be in the center. And as it goes to the maximum displacement, you see here it has energy. The energy is 0, because the question says we're talking about how much kinetic energy it has. Does that make sense? Yeah, because at the maximum, it stops, it changes direction, and we know it's moving the fastest when it's in the center, so it should have the most kinetic energy there. And as it moves back, it goes now in the negative direction, but it's still, energy is a scalar. There is no positive or negative values. They're all positive. And so when I get out here, I'm going to have no kinetic energy again, and it stops. As it moves back this way, it doesn't matter it's going in the different direction. It's still going to have the same kinetic energy. Now in this case, what is the amplitude of the motion? Well, it's going to have to be the maximum displacement, and if you read that from the graph, that's 5.0 meters. Now, what about the frequency? It tells me the time period is 2 seconds, so frequency and period are just inverses. And I have to have it in seconds if I want my answer frequency to be in hertz. Now the maximum velocity of the mass. Remember that equation I wrote at the beginning of this video. Plus or minus omega square root x naught squared minus x. What this is all about is, there's that angular frequency I've been just talking about. X naught refers to the maximum displacement, or the amplitude. And this says, where is it for a displacement? So in other words, I can calculate the speed of it anywhere during its simple harmonic motion, not just saying it stops at the edges and it's a maximum in the center. So if I put in my value here, I can have my frequency, so I can go and calculate omega. I can put my value of 5 meters for the amplitude. So I guess the only thing we have to think about is, where is the maximum velocity? Well, the maximum velocity is going to be at the center, where x equals 0. If you put that in, you can then calculate your velocity. Next part says maximum acceleration. Well, where is that going to occur? We've already said that maximum acceleration will be at the extremes, at the amplitude. And so I can use my equation, a equals negative omega squared x knowing that I can calculate omega with 2 pi f, and I can put that in there. Last of all, we have this sketch a curve of the total potential energy. So one of the things we want to point out is the energy is only ever going to be kinetic or potential. And as a physics teacher, I would panic if I don't have energy being conserved. So let's think about this. In the center, all it has is kinetic energy. It doesn't have any potential. And at the extremes, it has no kinetic energy and all potential energy. Okay? Now, the other thing is, if I add them together, here, 0 potential energy and this much kinetic energy, I must have this much total energy. So that's going to be the same at all these places. Now, here at the edge, I've just said there's no kinetic energy. It must all be potential, so it must be this amount right here. That's going to give me a graph that looks like this. That green one, this would be the potential energy. And if the question asked, I could also put another one in here, right along the top here, like this. This would be the total energy. So I hope that helps you out.